Okay, good afternoon, everyone. Let's continue our discussion on DNS. Just a couple of things left here before we move on to the other topic. So when we stopped last on Monday, we discussed DNS, how the database is organized in a hierarchical manner. Then we also looked at how the DNS system helps you to resolve the queries for getting the IP address corresponding to the domain name. And finally, we stopped with a discussion on the different types of resource records and how they are inserted into the DNS. Okay, so today we'll just continue discussion on a couple of optimizations or issues with DNS. So the first thing is, like every other distributed directory service, it would make sense if you can do caching for DNS queries, because for every web request or for every email request, every resolution for the domain name, we are going to contact the DNS system for the IP address. And since DNS query is one of the first queries that is launched into the network before any application starts, which uses these domain names, it is imperative that the DNS query latency needs to be optimized. Otherwise, it would add on to the application request latency. So a simple optimization that is used in DNS is to cache at different stages the mappings. So that means the name and the value or the key value pairs are cached whenever they have been resolved. So this caching helps you to reduce the overhead, because then in that case you do not have to contact the same TLD servers or same root servers again and again. If your local DNS resolver is caching the mappings corresponding to the most popular sites, it can directly serve the IP address from the local cache rather than again trying to contact the DNS system. Similarly, if the DNS, say TLD servers can cache the mappings or the information related to the authoritative server, then they do not have to contact the authoritative server. Instead, they can serve. So at different stages, this caching can be done, and it helps to reduce the number of requests. That is what we call as the overhead, and the total end-to-end delay that is perceived by the application. The key idea here is that there are small number of top level servers, and the TLD domains are also limited. The secondary TLD domains are also very limited. So all these are fairly static, and there are very few number of servers which are used to operate or administrate these domain names, and their mappings or their information. For example, the name server that hosts .com, it is not going to change often. So keeping this in mind, it makes sense to do the caching of this DNS information at different stages. Also, the domain names that you are going to resolve, mostly they are popular sites and they are visited often. So it again makes sense if you do the caching of the DNS mappings, because you are going to frequently use this. So this is similar to principle of caching deployed in any distributed systems. So there is high locality of reference, and then that basically helps you to reduce the number of requests that need to be sent on to the DNS system, and also reduce the end-to-end latency. So in a nutshell, if a name server learns the mapping and caches this mapping, and it can immediately return the cached mapping from the cache, then it improves the response time. It also helps you to reduce the load on the DNS system backend servers in general, and this helps you to reduce the end-to-end latency. One of the issues here, like with every other cache, is that how do you make sure that the entries are consistent or coherent, and cached entries may be out of date. The IP address domain name mapping might be changed. This is particularly more relevant when you have multiple replicas hosting the same website. The replicas might be down, or the replicas might be moved to different locations. So if you are having frequent changes of IP address, then the DNS system has to be updated with these mapping changes. And this is in general a tough problem. There are two approaches. One is invalidation of the cache explicitly. That means whenever there is a change in the mapping, it is communicated to all the DNS servers that there is a change, and that the cached entries should be invalidated or nullified. The other option, which is the soft state approach, which is taken in systems, is that you associate a time to live value with these entries, and once the TTL expires, then the mapping is automatically removed. So DNS design considerations, obviously these mappings are read only, because except the authoritative name server, nobody else can change or own the IP address corresponding to a domain name. This is well understood with the DNS. So with every response, whether the response is authoritative or it is not authoritative is also mentioned as a part of the flag. So if you get a cached entry or cached mapping from some cache, it is known to the DNS resolver that it's a cached request and it is not authoritative request. So to avoid this explicit invalidation, we use this TTL field, and every time the TTL expires, the cached entry is automatically removed. So again, there is a trade-off in choosing the value of the TTL. If you choose very small TTL, then it means that we are likely to change the mappings very frequently. If it is large TTL, that means we are going to keep the mapping fairly static for a long period of time. Large TTL would improve the cache hit rate and reduce the response time. Small TTL doesn't help you much, but then it helps you to change the mappings more frequently. So in the hierarchical system, in general, the mappings at the top of the hierarchy, like the root servers, the DNS, the root servers, and then the name servers, which are responsible for maintaining the TLD domains, they rarely change. So naturally, the TTL values for these are set for a longer period of time, like days or weeks. And at the bottom of the hierarchy, which is where you use the authoritative name servers and the mappings that are served by the authoritative name servers, these mappings are kept with a smaller TTL value. Okay, and then with the advent of these content distribution networks, there is also a practice of setting very low TTL values for all levels of DNS, and that helps you to keep doing the load balancing and also handle the failure scenarios. You can understand what happens if you are serving a cached entry, which is not just stale, but which also has probably the IP address has gone down, but you are still serving the IP address. So the machine is no longer there, but you are giving the same IP address, so the browsers would not be able to contact the machine anymore. And so this also poses a new problem for reliability of the system or the other applications in general. Remember, DNS is not just responsible for itself, but it is also responsible for all the applications that are using this DNS. So this is a trade-off between, there is a trade-off between how do you set the TTL values and how do you want to ensure load balancing and then fail safety in the system. Browsers also do cache these DNS entries for typically less than a minute. So we already talked about the DNS being the most important system behind every application. And to make sure that the DNS system is reliable, there are certain design principles that are used. First is the replication. So none of the DNS servers, including the name servers, are just located at one place. They are replicated. And the replication is also, it need to be handled properly. So you need to have some load balancing mechanism so that the replicas are getting equal load at different times of the day. This is again taken care by the corresponding name servers, which are giving you the mappings. So DNS supports mapping to multiple IP addresses. So when you try to resolve a domain name, you can also give multiple IP addresses. So typically Google gives you almost up to 50 to 60 IP addresses, in which case any one of those can be contacted, or the subsequent level applications can use load balancing to rotate across these IP addresses in a round robin fashion. Then since DNS uses UDP at the transport layer, UDP is a unreliable protocol, so there is no guarantee that your DNS queries are received by the corresponding servers in the first place. They can be lost, and because of this, it is the application's responsibility to take care of the reliability. So that means the DNS system itself has to have a mechanism to implement timeout So send a request and then wait for certain time. And after the timer's expiry, you will have to send the query again. So retransmission is done from the DNS servers itself. And before doing this retransmission, typically they follow this exponential backoff mechanism. That means you wait for some amount of time before trying the retransmission or sending the query again. And this time is doubled every time there is a failure. So that means first time you might be waiting for 2 seconds, then second time you wait for 4 seconds and so on. So this is to reduce the load of retransmitted queries again on the DNS system. Otherwise, you end up having lots of queries, including the fresh ones and the retransmitted ones on the DNS system. The other approach that is followed in recent times, because of the presence of multiple DNS servers responsible for serving a mapping, is that you are not targeting a particular DNS server for query, but you use something called as anycast in network. So anycast is essentially you pose a query to a group of servers, and anybody, any one server from that group can answer. So it is one of the paradigms for communication. Like multicast means sending the message to all the members of a group. Broadcast is sending to every server in the network. Like that, anycast is basically you are requesting the response to from any one server that can respond. So then the anycast query routing is the responsibility of the network service provider. So one can look at the nearest DNS server or the local DNS server which can serve this query and route the anycast query to the corresponding DNS server, and then you can get the answer from a nearby server or from any server which is active. So there might be multiple servers of which only few may be responsive or lightly loaded, and you can get the response from any one of those. Then also the system continues to work. Okay, so these are some optimizations that I just wanted to point. There are of course issues with DNS security. DNSSEC is a protocol which is implemented at least at the top level and the root servers to secure the servers from unauthorized insertion of resource records. So anybody arbitrarily cannot host a website and then insert the domain name, or you cannot hijack the mappings corresponding to a well-known domain by changing the IP address mapping and inserting a new resource record. So this is taken care by authentication into the DNS system with the DNSSEC protocol. Next, we will continue looking at other set of applications. These are not just applications, but I would say they are independent distributed systems or paradigms which are used widely nowadays to run applications. So it would be useful to look at these two peer-to-peer applications and what are known as CDNs, content delivery networks or content distribution networks. So are there any questions with respect to the DNS? Otherwise, we will move ahead with the other topics. Okay, so.
Sir.
Yes.
Does all the root servers contain same information or different information?
DNS servers?
Yes. Yes.
Okay. So DNS servers, all the roots have the same information. So the root servers are more or less tied up in tandem. So any one of the root servers will be able to give you information corresponding to all the TLD domains. So there are 13 of these root servers, as I was mentioning, 13 logical ones, but physically they could be, I think today there are about 225 different servers which are serving these 13 root servers. Similarly, TLD servers also, for example, the server responsible or a group of servers responsible for .in, all of them would have the same information, consistent information. So DNS, whenever there is an update in the record, for example, you have a new website or the IP address for a website has changed, the authoritative name server inserts it as a resource record into the DNS system. So that means you update it in the authoritative name server, and then there is a push protocol that basically pushes this database updates across all the servers. So these are like like database servers. All of these DNS servers work like database servers. So there is a consistency protocol which runs across all the DNS servers, which makes sure that the information that is there in one server is also propagated across the other servers in a similar hierarchy. That means you don't push every information all the way up to root servers, but wherever it has to be propagated, that is propagated uniformly across all the servers. Okay, so I didn't talk about the consistency protocol. DNS also has a set of consistency messages. Essentially, these resource records, whenever there is a change, there is a trigger that pushes DNS messages across these servers. Okay. The other thing you would have noticed in the iterative query or even the recursive query mechanism I was mentioning is that every DNS server, it can serve the response as well as it can also ask query to another DNS server. So in that sense, there is a daemon which acts as the server as well as the client. Okay. So in the recursive, you have seen that the TLD servers or the root servers do not pass on the TLD server's name, but instead they query the TLD server, then the TLD server queries the authoritative server, and finally they get the response and pass it back to the local DNS resolver. So the DNS by default has a client and server role. Okay.
Sir,
Okay.
why does
Yeah.
the IP address of a server changes?
Okay. Earlier it was not very common, but nowadays all the service servers, they at least subscribe to more than one ISP. Okay, for backup or reliability, right? So when you subscribe to more than one ISP, you naturally have two IP addresses, one for each internet service provider, right? And so if one of the ISP's link goes down, then automatically it switches over to the other IP address corresponding to the other IP. Other ISP. Okay, so that is one simple reason why the IP can change frequently. So suppose you are having an unstable link to one of the internet service providers. It like comes up every 4 or 5 hours and then goes down for half an hour. Then the IP address can keep changing rapidly. Normally, otherwise it is avoided. So those who run these services, they should make sure that they get a fairly stable IP. Otherwise, also DNS takes care of this consistency. So it is again the responsibility of the content service provider to make sure that the stale DNS mappings do not break the end-to-end connectivity. For example, if I am Google, I would have my own DNS system, and I would make sure that that system is updated with the correct IP address mappings. Or if I am subscribing to some service provider for giving me the DNS service, then I will make sure that the TTL values are low or kept in such a manner that they can reflect the changes in the IP address frequently. So for example, if I anticipate that my IP changes every 4 hours, then I would set the TTL only to say 1 hour or 2 hours rather than setting it to 24 hours. Otherwise, if you are a simple provider with just one ISP and then you do not have any other option, right? Then the IP doesn't change so frequently. Okay. Okay, then let us continue then the peer-to-peer. I hope you have come across the two types of applications or two ways of creating applications. One is the client server paradigm and the other one is the peer-to-peer paradigm. In client server paradigm, which is what we normally use for web browsing or file transfer and email and all these applications, most of the popular applications, we use this client server paradigm where the assumption is that there is always a server which is active, it is always on, and we know the server either by its domain name or by its IP address, and we know which server or where to contact for obtaining a file or a particular service. In the peer-to-peer architecture, there is no notion of an always on server, or there is no notion of having a designated server for giving the service. The peer-to-peer architecture is a general paradigm. You can think of implementing any application with peer-to-peer architecture. It doesn't restrict you for using only for particular architecture applications, but then there has to be some benefit or there has to be reason why you want to use this peer-to-peer way of designing the applications. Okay, so when we look at this peer-to-peer architecture, you would be able to understand some of the reasons why probably peer-to-peer application architecture would be required in certain cases. Okay, the first notion here is that all the devices that are running this application, they are peers. That means there is no question of a server taking more responsibility, the server being always on, and then the other users are only consumers. So it is like the entities are both consumers as well as the producers of the content. Okay. And then you can have arbitrary end-to-end connections between these nodes. Normally in a client to server architecture, all the clients connect to the server and the server is the only one that delivers the content. But here every node can request content as well as deliver content, or request service as well as deliver service. So peers not only request service from other peers, but they also have to provide service in return to the other peers. This definition makes the system highly scalable. What is called as self-scalability. That means as you add more and more peers into the system, normally in a client-server architecture, as you add more clients to the system, the load on the server increases and the system scalability goes down. That means the load on the system increases and the chances that the server will not be able to provide the right level of service, it keeps it basically goes up. But here, because of this peer-to-peer architecture, whenever you add new peers into the system, it increases the capacity of the system, and it can serve more service demands than what it used to serve with fewer peers. The only catch here is that peers are not designated servers. That means they don't have to be necessarily always remain active or remain on. So then this brings in challenges that how do you know which peers are active or which peers are currently serving the content. The peers can come and go, the peers can join, peers can leave the network, and the peers can also have change of the IP address if they are particularly mobile devices or connected to any system where the IP address can change. This makes the application architecture very complex in a sense that at a simple level you can think of the topology being changing in a continuous manner, right? So you don't know which machines are currently there in the network and how they are interconnected to each other and whom to contact now for getting a particular service. File sharing is one example where these peer-to-peer architectures are widely used, and they are also used in video delivery and many other applications nowadays. And this peer-to-peer architecture is also used in the backend in many of the CDN networks or content distribution networks these days. So peer-to-peer architecture is used in a big way, although as application users we may use only limited number of applications using this peer-to-peer architecture. Okay, so VoIP is one service that runs over peer-to-peer architecture in case of Skype. And there are differences between these architectures like BitTorrent and Skype. I will discuss only one of these peer-to-peer architectures, which is the most popular one, and the other ones are left for you to read upon. You don't have to know all the architectures, but in general, again, they are broadly classified as whether they use the centralized server or they don't use a centralized server in the system. So the general challenge in a client server architecture is that if you want to deliver a content, okay, so let us say there is a file of size F, and if you want to serve it from one server to say n number of clients, see this picture. It basically shows how the networks in general are restricted with the upload and download capacity. So every server, however powerful it may be, ultimately it is connected to the network, and the network connection has certain bandwidth, and that bandwidth determines what is the server's upload capacity. That means the rate at which it can serve the content to the requesters or the clients. From the client side, you can call these as clients or peers. When it requests some content from the server through a network, there is a download capacity which is shown here as DI, and when it has to upload certain content, let us say you are sending an email or you are submitting a form or you are uploading an attachment to some server, then you are doing this upload function through the network, then there is a again upload capacity. So these upload capacities and download capacities are determined with the upload bandwidth and download bandwidth that you have for the network subscription link. So normally servers are subscribed to very high speed internet and they are positioned in such a way that their upload capacity should not get limited, but then nevertheless the capacity is always going to be limited, and that will determine what is the rate at which you can serve the content to n number of clients as this n keeps increasing. So in general, client server architecture will always do sequential transfer. For example, if the first client comes and requests for a file of size f bits, it serves that file to that first client and then goes with the subsequent clients. So every time it has to give the entire file copy to each and every one of these clients. So essentially what you are doing is you are doing n times unicast communication with each of these clients, right? So you are sending n copies of the same file again and again to each one of these clients. So the total size of data that needs to be sent is n times f, where f is the file size, and this needs to be done on a link with capacity US, right? So US is the capacity of the link, which we called in the previous slide as upload capacity. Okay, so NF by US will give you the total time that it takes to send n copies of the file on a link with capacity US. So from the client side, you are having dmin is the minimum client download rate, and if f is the file size, then f over dmin would give you the total time taken to download this file from the client's perspective. Now, what is the total time or the time minimum time that is required to distribute this file to n clients using the client server approach? It is going to be limited by the maximum value of either nf by us or f by dmin. Okay, so as n increases, you are basically going to have a lower and lower throughput per client, not because of the client side's restriction, but because of the server side restriction. This is one very important characteristic that you should always remember. Even though the client side bandwidth may be unlimited, you may have 1 Gbps or you may have 10 Gbps rate, but it may not still help you to get the file in a whatever 1 Gbps or 100 Mbps rate, primarily because of the server side upload capacity limitation. So every server, if it's a single server model without any replicas or without a method for doing load balancing or distribution of the client requests across different servers, then it is going to eventually choke at the server end and not at the client end. So in peer-to-peer, what happens is that every peer will be able to contribute to the resource. So the server basically will have to upload only one copy. So once the server serves one copy to one of the clients, assuming that this client's information is available with the other clients, the client can download the file copy either from the server or it can download it from another client, or it can also do it in parallel. That means the file, half of it can be downloaded from one client and the other half can be downloaded from the server. So aggregate, we only talk of downloading again NF bits, where n is the number of clients and f is the size of the file. Now what happens here is that the time to distribute this file f to n clients using a peer-to-peer approach, there are three components. One is the individual, the client's download rate, which is given by f by dmin. The other one is time taken for the server to send one copy of the file, which is f by us. And the third one is nf upon us plus sigma ui, where sigma ui is the, or us plus sigma ui is the maximum upload rate that is contributed by all the clients or all the peers in the system. The way this works is that every client, once it starts getting the file, it also starts sharing this file with the other clients. So the pieces or the bits that it already has downloaded from the server, it also starts contributing in the upload direction to the other clients. And this is what increases the capacity of the system. So as n increases linearly, you still have the problem of load on the server side, that is nf is anyway going to increase, but also the total service capacity of the system is going to increase because of the summation of ui part where I goes from 1 to n. Okay, so this is just one plot of these functions. The minimum distribution time, how does it vary as the number of peers or as the number of clients in the system increases? It scales linearly with in a client server system, but in case of peer-to-peer system, there is a sublinear growth. That means as the number of clients keeps increasing, you will not have such a steep time increase in the distribution time. So you will be able to complete the the file transfer faster as you have more and more clients in the system. We will see how this works with a simple example of discussion on the BitTorrent architecture. This is just one of the architectures which is used for peer-to-peer networks. There are other architectures. BitTorrent uses a tracker-based mechanism. So basically, there is a tracker which gives the information about the peers participating in the system. That means whenever a peer joins in the system, it is registered with the tracker. So that way the tracker knows some basic information like what is the IP address of the peer and what files does it currently have. Okay, so this is something similar to what you must have used on campus like the DC++ or the other such systems which are out there. There is basically a tracker which keeps record of the peers in the system and what files or what content they have with them. So once this is there in the system, it becomes easy to locate the content. Okay, so essentially this tracker helps you to bootstrap to the system. Whenever a new peer joins, it contacts the tracker, and then the tracker will give you the information about what are the other peers in the system, what are they sharing, and then what files are available with them. And then the client can start requesting it into the system, and this can be served from multiple peers in the system. So for this to work, the content is basically divided into smaller chunks. Typically, the BitTorrent chunk size is 256 kilobits long, and the peers in the torrent operate on the content in the file chunk sizes. That means they upload or download the file in units of these chunks. The word torrent basically indicates the group of peers that are exchanging the chunks of a particular file. So all the peers which are exchanging one particular file, they are all part of a torrent. Okay, so there are multiple torrents in the system, and each torrent or each swarm of these peers essentially is doing the content exchange with respect to one file or one piece of content. So a new peer arrives, it gets the list from the tracker and then begins exchanging file chunks with the peers in the torrent. Okay, so you need only IP address of the system, and maybe if there are some authentication, then you need to get that information. So peers join the torrent. So whenever the peers join, initially they do not have any content with them. So they only join as new joinees, and then once they start downloading the chunks, they will also start accumulating these chunks over time from other peers. And whatever is downloaded from the peers, it is also shared with the other interested peers who are looking for the same content. So it registers with the tracker to get a list of peers, connects to subset of the peers which are called neighbors in the peer-to-peer architecture. And then when you start downloading these chunks, you also upload these chunks to other peers. And peer may change peers with whom it exchanges the chunks based on the bandwidth that it is getting or based on the download rate that it is getting. And churn is an important characteristic of peer-to-peer architecture. That means there is no time for which the peers must remain in the system. Peers can come and they can always go. And this gives you selfish behavior in the sense that whenever a peer has downloaded the entire file, it may leave the system, or it can remain in the system and keep serving the other peers in the torrent. So both behaviors are possible. So BitTorrent has a mechanism for incentivizing the time that is spent in the peer-to-peer system. So that is tit for tat strategy, as the designers called it. So whenever you request chunks, you are basically doing it with a subset of these file chunks, and whatever chunks are missing from the peer from your file content, they are retrieved from the other peers. And normally the scheduling approach that is followed in the BitTorrent is that in scheduling these chunks for upload or download, the rarest chunks are always served first. So that means the chunks which are present with limited number of peers, fewer number of peers, they are always served and replicated faster compared to the other chunks. So this makes sure that the the chunks which are available with a fewer peers, they are eventually available with all the peers. So it improves the content popularity. Okay, and then there is a choking mechanism which basically tracks what is the rate at which each peer is uploading the content, and based on the upload rate, the download rate is also decided. If there are the selfish peers, their download rate is slowly choked by the system, and the system eventually makes sure that unless you share content, you will not be able to get new content from the other peers. So this is the tit for tat strategy. So Alice, optimistically unchokes Bob, and then Alice becomes one of the Bob's top 4 providers. And if Bob reciprocates, then Bob also, remains as one of the Alice top 4 providers. Otherwise, he is thrown out of the system. So the idea here is that higher the upload rate, you will also, get the content in a faster manner from the other peers. Okay. So the other architectures which are which do not use a tracker, because one issue with this tracker based systems is that suppose somebody wants to block a torrent system, it becomes easy if you can block the torrent block the tracker. So once the tracker is down, then the peers in the system will have no way of detecting who are the current peers and what is the content that is available with them. To avoid this, there are other decentralized peer-to-peer systems. They use a system called CORD, which basically has a way of organizing the peers or the peers addresses in an address space, and then there is a designated way in which the peers identify their neighbors, and through these neighbors they send the messages to the other peers in the system, and they can do the query and responses. So this quad is another distributed peer-to-peer architecture which doesn't require a tracker, and it can still function like the peer-to-peer architecture. Uh, then of course there are these hybrid architectures which use a combination of servers and peer-to-peer. Skype is one such architecture. Skype uses nodes, designated nodes called as super peers or servers. These are some always on servers, and then the new peers which join into the system, they contact one of these servers and get the bootstrapping information, and they can also route their queries through these relay nodes or through these designated server nodes or the super peer nodes. So there is a hierarchical architecture. There are ordinary peers, and then there are super peers. So the super peers are kind of more powerful machines, or they are always on, or they are likely to be hosted by a content provider. And then the other peers can come and go, but the super peers will always remain in the system. They help you to bootstrap to the system. So these are some of the other architectures which are used in the peer-to-peer systems. We will then discuss with client CDN. So any questions on peer-to-peer? Okay. Okay. Next, we will look at the content delivery networks, or sometimes they're also called as content distribution networks. These are again very widely used since now almost 2 decades. In fact, their importance was known only after the 9/11 attacks in 2001, when there was massive traffic on service providers like CNN, BBC, and other such news providers. When there are flash crowds, which means there is a sudden upsurge in the number of clients that are hitting your system. And when this happens, the any kind of replicated infrastructure is likely to fail purely because of the volume of the client requests that is suddenly hitting. Now, if you try to cater to this volume throughout the year, you will end up wasting a lot of capacity, waiting for the flash crowd or waiting for the popular event to occur. And this is when people realize that content delivery is not an easy job, and you do not just need one server or a group of servers for content delivery, but a systematic infrastructure which can do all the tasks that you want for a reliable replicated system, like caching, replication, routing the requests efficiently across the replicas, replica management, then reliability aspects, and of course, ultimately giving high upload rate, getting high upload rate for each of these servers in the content network. And then, of course, in the last decade, video became the major traffic, or video became the major application. And nowadays, there are not just streaming. Streaming video is not only used in entertainment, but also in news and all the other applications as well. Video has become one of the most popular content, and every content provider has to support video content. And video is supposed to be, or it is the consumer of largest consumer of internet bandwidth, and it would continue to remain the largest consumer at least for the next decade. That is what people foresee. So Netflix, YouTube, Amazon Prime, all of these together contribute to about 80% of the residential ISP traffic, is what a survey in 2020 shows. So how do you reach 1 billion users who, let us say, would all want to watch video content at the highest rate that is possible, or highest quality that is expected by the end user? The main challenge in the networks, which always is going to continue to remain with us, is that different users have different capabilities from the end side, that means from the edge network side. They can be connected to the wired network, they can be connected to the mobile network. You could have a bandwidth rich network, or you could have a poor bandwidth network. The devices themselves can come with different configurations. So all this makes the content delivery a challenging task. So what these CDNs have started is to give a distributed application level infrastructure, which kind of overcomes the problems existing with the network infrastructure that we have. So all of the major video content providers, they have their own CDNs, or they resort to third-party companies called as CDN providers. Akamai is one such CDN company. So Akamai does only content distribution network on behalf, content delivery on behalf of all the other content providers, whereas Google has its own CDN, apart from being apart from serving other things, or apart from giving other applications. There are so many such CDNs now. The most popular ones are Akamai and then Limelight. So before that, I'll just talk of video. What happens with video delivery over the internet? You are all aware that video is a sequence of images which is displayed at a constant rate, typically say 24 images per second or 24 frames per second. Video can be represented as a digital image, as an array of pixels. Each pixel is represented by bits, and then to reduce the number of bits that are used, or they reduce the size of these array, people use a coding strategy, which is also called as compression. There is high amount of redundancy within an image. That means if you see, for example, there is a lot of purple shade in the image, and this purple shade, is uniform throughout several regions of the image. So you can reduce transmitting it, encode it with fewer bits, and then say that, okay, for all this region there is purple color. And across images also there is high amount of redundancy when there is not much of motion, when there are static images or limited degree of motion between the frames. You can have again some redundancy. You don't have to transmit all the frames accurately. So there is spatial redundancy that is within the image, and there is temporal redundancy, which is the redundancy between two images in a video. So taking an advantage of this redundancy in spatial domain and the temporal domain, people tend to, or the encoders tend to send only the difference between the frame I and I+1 in the temporal domain, or within the frame I also the only the difference is encoded, and the other part is kept constant. So video is of two types: whether the encoding rate, that means the rate at which this encoding is done, whether it is fixed or whether it is variable. So constant bit rate video stands for video encoding rate being fixed, and variable bit rate video, the video encoding rate changes based on the spatial, temporal, and coding changes. So it's an adaptive process based on the richness of the pictures or richness of the motion. The encoding rate changes. So VBR video is most popular one that is used now. It gives you higher level of compression and better encoding efficiency as compared to the CBR standard. But VBR makes it hard because you will have to also encode the rate along with the amount of encoding or amount of compression that is done. There are these different standards by MPEG, and MPEG 4 is what we use often in internet for transmission. Because of the variable bitrate encoding, one interesting property of this video is that the size of the video frames or size of the video that is delivered per unit time, it can change very drastically between say a few kilobits per second to all the way up to tens of megabits per second, based on the richness of the content or based on the changes that is there in the content. Otherwise, in constant bitrate video, you would have a steady rate of the video being delivered. So CBR is very easy to deliver over the internet because you have the rate at which the video is going to be transmitted is fairly fixed, and you can plan the network bandwidth according to the rate at which the transmission is done or the encoding rate. But because the encoding rate is variable in VBR video, you would not be able to estimate what is the minimum and what is the maximum rate which is required for video transmission on a particular network link. Okay, so when you talk of say 720p, 720p or say 360p, it is the encoding rate, but the content size itself keeps changing based on the richness of the content. Anybody has to say something? Okay. Okay, so the basics of this streaming, this stored video, which you are, we all use, streaming video day in and day out. It's there on Facebook, it's on YouTube. Every, content provider now has lots of video content, and we consume a lot of video. So there are three elements in this streaming stored video. One is that there is a server where these videos are stored. I'm talking of stored video. I'm not talking of live, but the architecture is similar. Even if you have live video, you would basically record the video first through cameras and then encode it and then push it onto a video server. And from the server, it gets served on the over the internet to the client. So the main challenge here is that the client to server bandwidth can vary over time because of the changing congestion and changing network conditions. So you may have congestion because of the other traffic that is there. Either it could be inside the same house or inside the access network or core network, or because of the load on the video server, you may have different congestion levels across the end-to-end path. Apart from this, the other challenge is that you can also have the video rate being varying widely, drastically over time, depending on the content. So for example, a sports video has more, it consumes more bandwidth as compared to the news video. It's a very known fact because of the MPEG compression itself. So all these cause packet losses, then delay due to congestion, because congestion causes, as you are aware, queuing in the network. So there is queuing delay. Queuing delay is what makes the end-to-end delay completely random, and it makes it fluctuate drastically. And this delay will cause delay in the time at which this video content is delivered to the client and subsequently played. And this results in poor video delivery quality, or poor playback quality. And you are all familiar with interruptions or stalls in video playing. Whenever there is no content in the buffer for playing, YouTube basically stalls over it, and then whenever it gets sufficient content again into the buffer, it starts playing. So all this happens because of the backend congestion in the network. It could happen anywhere in the end-to-end path. So essentially, we can represent this streaming stored video problem as the following. So if you look at in the y-axis, it shows the cumulative data. So you can see this, the steps that you see here are basically the packets that are coming periodically. So this is from the delivery side. So when the video is being sent, let us say 30 frames per second or 24 frames per second, it corresponds to some amount of data. Let us say say 100 kilobytes every second. So if it's 100 kilobytes, so you are getting 100 kilobyte packet every 1 second, and this is sent from the video server side. Assuming there is no problem as far as the processing speed is concerned, the video can be sent at a steady rate from the server side. What happens at the client side is that once the video is sent from the the server side at a steady rate, which is what is shown in the red color line here, then we are assuming if the network delay is fixed, that means if the end-to-end delay between the server and the client is exactly 100 milliseconds, after every 100 milliseconds, you should be able to play one packet. So the packets are sent at a particular rate, and at the same rate, the packets should be arriving at the client, and they should also be played at the client in the same rate. This is the ideal scenario if the network delay is fixed without any variable component in it. But what happens, as you all are aware, is that there is a queuing delay component which gets added to the transmission and the propagation delay. And this queuing delay makes it widely variable, and this causes the packets not only to arrive at different times, but the inter-arrival time between the packets also can largely vary, which is called as the jitter in the network. So due to the jitter, you will not have the video frames being played at the same rate as at which they are being sent from the server side. Okay. So we'll stop here, and in tomorrow's class we will continue discussion of the basic framework used for video playback, and then the CDN architecture.